Welcome to the i-ROM Model Builder tutorial. In the last video, basic functions of a modal analysis have been demonstrated. In this tutorial, we will show the effects of manufacturing tolerances on the results of the modal analysis. The user model input file defines nominal dimensions of the accelerometer example. Mask undercuts, and various deviations in the sidewall etch, occur during the manufacturing process. Dimensional imperfections can be easily assigned in the process data window of the model builder. In the following example, a mask undercut of 0.2 micrometer and a uniform sidewall etch offset of -0.5 micrometer is assigned for demonstration. Positive values make the silicon structures smaller, negative values make the silicon structures wider. The mask undercut affects all the top faces, and the offset data for the sidewall etch affect the bottom edges in the specified directions. A spring with a nominal width of 3 micrometer becomes a trapezoidal cross-section, with a width of 2.6 micrometer at the top, and 3.6 micrometer at the bottom. To improve the fracture strength, corner fillets with different radii can be applied to spring and spring mask connections. Typical values are between 2 and 3 micrometers. The model builder also supports local data for etch settings and corner fillet radii at individual model items. Click Now Build Solids and review the new changes. Click Build ROM to create a new simulation model, and perform a modal analysis. Without the process data, the first eigenvalue was 13.3 kHz, and now it is shifted to 14.5 kHz, which corresponds to a difference of around 9%. Imperfections in cross-sectional data cause coupling effects between motion degrees of freedom. Manufacturing tolerances have a strong influence on the accuracy of inertial sensors, and must be quantified before manufacturing. Let's look at the first eigenmode. The amplitudes in the y direction are scaled to 7.8 micrometer. It produces approximately 65 nanometer amplitudes in the out-of-plane direction. The mass body rotates slightly around the x-axis. Torsional vibrations are caused by the trapezoidal cross-sections of the Timoshenko beam elements. The center of gravity is higher than the shear center, which results in a torque with each oscillation cycle. The next step is to analyze the influence of asymmetrical cross-sections. Change the sidewall etch offset for south-facing areas from -0.5 to +0.5 micrometer. Press Build Solids, Build ROM, and redo the modal analysis. Now rescale the model. The cross-sections of the beam elements become a parallelogram with 2.6 micrometer width, whereby the bottom areas are shifted 0.5 micrometer north, compared to the top faces. The first eigenmode in the y direction now generates a transversal motion component of 141 nanometers in the z direction. The crosstalk values can be quantified with the eigenvector components at the center of the mass body. The physical reason is a misalignment of the major axis in the area moment of inertia. In the i-ROM Model Builder, manufacturing constraints can easily be applied and changed depending on the underlying process parameters. This allows you to assess the accuracy and yield of new sensor products. I hope you enjoyed this video. The next tutorial introduces the modeling and simulation of electrostatic softening effects in a modal analysis.